Welcome back to the course of probability theory. Last time we made a small recap on measure theory, and this time we are going to continue this a bit, and we will also continue to recall things from probability which you might already know from your basic course, which are moments like the expectation, variance, covariance, and so-called characteristic functions. They are part of some of these basic courses, but not all of them, so they might be new. But they are very helpful, in particular for computing moments and other stuff which we will cover later in this course. So let's get started. Moments, characteristic functions, and the third thing, which I did not mention in my introduction, are Laplace transforms. These are things which are similar to characteristic functions. So let's start with moments. You might know them. We said that we always have a probability space, omega fp, and the expectation we said e of some x, which is a function from omega to maybe r or something, is defined by the integral of x of omega p d omega. You can say this. So that exists if the integral exists, and this exists if the absolute value of the integral here, so integral of the absolute value of x p d omega, exists. And then we call e of x the expectation or expected value of x. And the variance is something similar. It's also an expectation. And you might recall this from your basic probability course. So that's the mean because this is the expectation, quadratic because that's a square here, the mean quadratic difference of x with its own expectation. Okay, and the covariance of two random variables x and y is this here. So it's also the mean difference between the product of, the differences of x and its expectation and y and its expectation. You might also remember that if covariance is 0, then x and y are called uncorrelated. You might also recall that you cannot only compute the expectation of x, but also of x to the power of p. That's called the pth moment. And if you subtract the expectation here in the bracket, then you have the centered pth moment. You might recall from a course on measure theory that there are these LP spaces. And in the LP space, you have all random variables such that e, the expectation of x to the power of p, exists. Okay, that were only definitions. And there are usually several properties of variances, for example, on this slide that you compute. For example, this one here. And let me just recall this, how this comes about, so how you can compute this. But that was certainly part of your basic probability course. So by definition, that's the expectation of x minus expectation of x squared. I can compute the square in the bracket. Then I have x squared minus 2 times x times expectation of x plus the expectation of x squared. Well, and here you're integrating, for example, over a real number. So you're integrating over a constant. And what does this mean? You're integrating a constant over a probability measure. The probability measure has total mass 1, and the result is just the constant. So the outer expectation I can just ignore. And the same here, so expectation of a sum I have here. I think I did some brackets wrong here. Okay, so I did some brackets wrong, I think. So this expectation is basically not there because this square here is the square of this here. But I have linearity of the expectation, which means I can pull apart this term here in the bracket. And the last term is expectation of x squared, and there the argument I just gave applies. The first thing here, expectation of x squared, okay, that's also in the result here. Then I have expectation of minus 2x, expectation of x. And here again, expectation of x times expectation of x. Well, I have linearity of the integral. I can take the expectation of x out of the integral because it's linear. So expectation of x out times, well, what remains is again the expectation of x. So I have expectation of x squared. So expectation of this here leads to minus 2 expectation of x squared. And again, I have a plus this here, which then goes into the minus here. Okay. And then we have the Cauchy-Schwarz inequality, which we already had also last time, which was this inequality here. Now it looks a bit different because I have covariances here and I had expectations last time, but the covariance, remember, it's only an expectation anyway. And when you plug in x minus expectation of x and y minus expectation of y instead of x and y here, you come up with exactly this equation, which is then the Cauchy-Schwarz inequality. One other thing which you will need often is that the variance of a sum can be computed differently. Okay, if the variance would be the expectation, I would just say, well, expectation is linear. So expectation of a sum is the sum of expectations. It always holds. Not so much for the variance. The variance of a sum is not the variance of the expectations, but sum of the variances plus sum of all covariances. And the reason is that the variance of the sum here is an expectation of a square, so you have to square this here, and a square of a sum is a double sum, and that's essentially what happens here. So one part is in this and one part is the covariances here. Okay, let's compute a bit more. There's one trick to compute expectations, which you might remember from basic probability, and this is also elaborated here. So instead of integrating x of omega over p d omega, integrate here over dt something. And if p equals 1, for example, then I have expectation of x is the integral over the probabilities that p is x, that x is bigger or bigger than equal than t. You might recall this. So let's compute this also. And the trick is to use Fubini's theorem. And first of all, write x to the power of p more complicated, which is the integral from 0 to x t to the p minus 1 dt times p. So when you integrate this here, you have t to the power of p in the area from 0 to x, which is exactly x to the power of p. So that's just written more complicated. And I'm doing this because the expectation here, that is an integral. That's also an integral, and Fubini's theorem tells me that very often I can exchange them. I need one more step in between. Because, let me just try like this. I integrate from 0 to infinity, t to the power p minus 1, indicator function x bigger than t dt. So that's the same integral. And now I can exchange the integrals. Integral, so I'll write down up the p, integral from 0 to infinity. T to the power p minus 1 I can write down here. And then I have the expectation of the indicator x bigger than t dt. And this one here, the expectation of an indicator is the probability of the set, like this here. And that's already it, because that's exactly this equation here. And that's sometimes very convenient in order to compute expectations. Let me just recall one computation here. So if x has, for example, exponential distribution with parameter lambda, which means that the probability that x is bigger than t equals e to the minus lambda t. And then I can use this here, for example, to compute the expectation of x. That's the integral from 0 to infinity over e to the minus lambda t dt. And this is 1 over lambda. And you can also do that, of course, on a different route. For example, by using the density of the exponential distribution. But this here is just very short and very simple to compute. Then let's go on to these characteristic functions. And later we will learn why they are called characteristic. Now I'm just giving them in some sense. So psi x of t is called characteristic function, and it's defined by the expectation of e to the power itx. And when you look at this, you might be confused because I is the imaginary unit. So this is a complex number here in the expectation. And up to now, we only defined the expectation of random variables which are real valued. And here I have a complex valued random variable. But that's not a problem. For one, I can make the integral more general by the so-called Bochner integral. But it's the same to say, well, I have an imaginary thing, but essentially what is an imaginary number? It's a real part and it's an imaginary part, and both are real numbers. So I can just define it like this here, expectation of cosine plus expectation of sinus tx. Okay. And just for notation, x was here rd valued. Very often we will only compute this for r valued random variables. So here's rd valued, and tx means the scalar product of t and x. So t here in this case is also in rd. So the characteristic function is a function from rd to the complex numbers. Then the Laplace transform is something similar. The only difference is here I have the I and here I do not have the I. So the expectation of e to the power minus tx. And very often this here is only computed if x is non-negative, because then I know that this function here is bounded and it always exists. While the characteristic function, it always exists, because e to the itx is a complex number which always has absolute value 1, which means it's bounded. So this always exists, and this here only exists certainly if x is bounded from below. Okay, so why are they useful? Let's do some properties of this here. So they will be useful because later we will learn that there's a certain aspect of convergence such that we can say random variables converge if and only if their characteristic functions converge. And characteristic, what does this mean? It will mean, we'll not do this today, but later in the course, that the characteristic function of a random variable uniquely determines its distribution. So the characteristic function is characteristic for the distribution of x. And that's the main reason why that's so useful. So let's do some properties here. Okay, some simple ones. For example, cx of 0 equals 1. Well, why is that? If I have a t equals 0 here, I have e to the itx, e to the 0, which is 1. Expectation of 1 must be 1. So that's easy. So that's straightforward. Also, this here we already had the absolute value of cx of t. Like this here, absolute value. Well, it's bounded from above by the expectation of absolute value of cos plus expectation absolute value of sine. And by using, for example, also here, the absolute value of this here is smaller or equal than the expectation of the absolute value here in the brackets, and this is 1. So that's also very easy. And the third thing here, psi is uniformly continuous. I'm going to prove this in a second. And the last thing here, that's also easy because, well, let me briefly write this down. Psi ax plus b of t is by definition the expectation e to the I t ax plus b. And now I can say, well, I to the minus etb. Sorry, that's not a minus, that's a plus. There's no minus here. I can pull it out of the expectation, I to the etb. And here I have e to the power of itax, and that's the same as saying I have the characteristic function of x at a times t, times psi x of a times t, like this here. And that's also easy. Now let's come to uniform continuity. And for this, we need some bound of this here. Well, we need this. This here is that has some property. So let's compute it. So the absolute value of a complex number, that's square root of, well, I have the real part and the imaginary part of this number. The real part is cos of hx minus 1 square. The imaginary part is sine of hx square. Which means I have cos square plus sine square, which is 1. I will get another one from the square of this one here. This will give me then a total of 2. And all what remains is minus 2 times cos. So 1 minus cos hx, and this is it. there are all these formulas for the cos and sine, and I can tell you what this here is. That's the same as under the square root, something like 2 times sine square. When I take the square root, I get absolute value of sine hx over 2. Sorry, this here. And now I can bound that from above, so sine is smaller than, sine of x is smaller than x. So that gives me an upper bound of hx. And it's of course also bounded, the sine is bounded by 1, so that means this here. Okay, I claim psi is absolutely continuous. What does this mean? So continuity would mean if I have psi x of t plus h minus psi x of t, that goes down to 0 if h goes down to 0. And if I have that uniformly for all t, I call this uniformly continuous. Let's first write down what it is. So super all t, I write up expectation of e to the I t x e to the I t h minus 1. I write like this here. So first of all, psi x of t, that's the itx, e to the itx minus 1 times 1 is minus 1. And here, sorry, that was wrong. That's not ith, that's ihx, of course. Because when I add this up here in the exponent, I have it plus hx. Let's also make the absolute values. I can bound it from above and write the absolute value inside the expectation. Then I get the absolute value of e to the power of itx, but that is 1. And then I have ihx minus 1, like this here. And we already see now we deleted the t, so t doesn't come up anymore here, which means I can also delete the sup here because it doesn't play a role. And for this here, we already saw that's the expectation, so it's more or equal than the expectation of hx minus 2. And this here goes down as h goes to 0 because dominated convergence tells us so. Okay. So that's not a minus 2. That is a maximum 2, of course, like this. So this function here, if h goes down to 0, goes down to 0 point-wise. And if a function, so if a sequence of function goes down to 0 point-wise, does the expectation of these functions also go down to 0? Well, not necessarily. We need a convergence result from measure theory. And dominant convergence tells me I need a dominating function, and that function here is the 2, and 2 is integrable with respect to the probability measure because it has an integral of 2. So I have all the conditions of my dominating convergence, which means that here goes down to 0, and we have proved uniform continuity. Okay. Let's make some examples. Well, sorry, there's a typo here. So x is binomially distributed. Let's compute the characteristic function. So that's also an exercise of computing any expectation at all. So some k from 0 to n, k choose n, p to the power of k, 1 minus p to the power of n minus k. And then I have e to the itx, so e to the itk. And we see here we can combine something, p to the power of k and e to the itk. I can combine, so p to the k times e to the itk is the same as p times e to the it, and this to the power of k. And when I do this, I again can use the binomial formula, and I end up with, well, 1 minus p plus p e to the it to the power of n. So in particular, there is no sum involved anymore, which is nice, because then I can compute things easier with this. And also for the Poisson distribution. So what's this expectation here? E to the power minus gamma, sum gamma to the k divided by k factorial, sum k from 0 to infinity, times e to the itk. And the same trick applies here. Gamma to the k, e to the itk. I can do the same thing as above here. And I have here again some e to the power of something. And what's the something? E to the power of gamma times e to the it. And in total I get e to the power of gamma e to the it minus 1, like this. Okay. Again, without any sum, which is nice to compute things in the future. But this is not all. I can also use this with random variables which have a density. So first of all, normal distribution. So what's the characteristic function of x if x is normally distributed? And you might also note here that sometimes I write an x here in the index. And here I also write the distribution. And how was it defined? Yeah, like this here. So either write x or the distribution of x. And the reason why I do this is it only depends on the distribution of x and not on x itself. So let's compute something for the normal distribution. Well, and I only do this for mu equals 0, sigma squared equals 1, because if z is n01 distributed, then sigma set plus mu is n mu sigma squared distributed. And we had this one property. If I have the characteristic function of x, and I want to have it for ax plus b, I have an extra term e to the ibt, and I've evaluated at not at t but at a times t, and that's exactly what's happening here. So mu is here additive, and that's the extra term here. And I do not plug in t, but sigma times t. So when I computed for mu equals 0 and sigma squared equals 1, I have computed the full thing here. So let's try to compute psi n01 of t. By definition, this is 1 over square root of 2 pi integral over e to the minus x squared divided by 2 times e to the itx dx. Okay. But now I'm doing a trick, because that's not easy to compute. I'm making derivative with respect to t. I have to also do that on the right hand side. And here that means I have to make the derivative of this here, and this gives me an I times x. So the I I'm writing down here, and the x I'm writing down here. And now I can use integration by parts, because this here is a derivative, or minus this one here is a derivative. So I have to say something like, well, if this here is an u prime, this here is a v, I rather integrate over the other way around, so u times v prime. And what is v prime? Okay, it comes to the bottom, and everything stays. So the I times t, the I times t here, together with this I here, gives me a minus. Exactly. I also have a t, right? And for all the rest, I have 1 divided by square root 2p integral without any borders, e to the minus x squared over 2, e to the itx dx. And you realize here that's the same as minus t psi n01 of t. So what I found out now is that the characteristic function of the normal distribution satisfies the differential equation, which is exactly this here. And, well, I can solve this initial value problem. I know from general theory that there's at most one such solution. And the solution is psi n01 of t equals e to the minus t squared over 2. Because when I make the derivative, I get an extra factor minus t on the bottom from differentiating t squared over 2, which gives me t, and the minus also. So this here solves this initial value problem, which means that must be the characteristic function of the standard normal distribution. Okay. Last thing. So one Laplace transform. I said that Laplace transforms are mostly computed if x is non-negative. And one example is, again, as we had before, the exponential distribution here. Well, let's write it down. From 0 to infinity, the density is gamma, is gamma times e to the minus gamma x. And then I have to use e to the minus tx for the Laplace transform, dx. You can compute this. Here you have minus gamma plus t to the power of x. And the result is, when you do this, gamma divided by gamma plus t. Also very easy, no integrals. Okay. Characteristic function and moments. That's what I said at the very start of this video. that there's a nice connection between characteristic functions and how to compute moments. And the answer is, if you have the characteristic function here and you make the kth derivative at t, what you get is this expectation here. So that's again exchanging integral and derivatives. And if you now say, well, let's use t equals 0, this one here goes away, and you have the expectation of some factor times x to the power of k. So the kth derivative at 0 is very close to the kth moment of x, which is nice, of course. Yeah, so I can compute this iteratively, so by induction or something. If k equals 0, I have the 0th derivative, which is nothing, and then that's just the definition. And if it holds for some k, so if star holds for some k smaller or equal than p, yeah, so if x is in LP, so it now holds for some k smaller than p, then I can compute it for k plus 1 x of t. So I can interchange. So first of all, the k plus first derivative is the derivative of the kth derivative. For the kth, I already have the formula here by assumption. So I make d by dt ix to the power of k e to the itx. And now that's not really hard. I have to compute the derivative. And the d by dt of this here just means I get one additional factor I times x, which is then I times x to the power of k plus 1 e to the itx, like this. And I'm done. Okay, here plug in 0 gives nothing new. And yeah, well, we'll need this if x is in L2. So the moment of x square exists. Then I can say, well, epsilon is something small, maybe. Or t is something small. So what happens? I get, like in a Taylor series, I have psi x of 0, which is 1, times the first derivative, which is I times the expectation, times t in the Taylor series. Then I have a t squared term. And then I have something which vanishes. And then in the t squared term, I have the expectation of x squared, and the minus comes from the two factors I, which I have here. Okay, so that's for the general theory of characteristic functions. And let's just make some or two examples. So let's use the Laplace transform, and let me note the calculation for the Laplace transform is very similar to the calculation of the characteristic function here. And compute the nth moment of an exponentially distributed random variable. How does that work? I mean, in the characteristic function, I have for the characteristic function, I had psi x of t is the expectation e to the power itx, right? And for the Laplace transform, and x of t, I had expectation of e to the minus tx. And that's essentially also covered here, because all what I have to do is to say, well, for t, I'm using it. And then I times t is just minus t here. So I want to say that the Laplace transform at t is the same as the characteristic function at I times t. So, well, but maybe also directly, the nth moment, how do I compute this? Make the nth derivative of this here. I have n times going an x in front of the power here. And I have to correct for the number of minus signs. When I do it minus n times, and I multiply by minus n to the power of n, I will certainly get a plus sign in the end. We already computed the Laplace transform of the exponential distribution, which was here, gamma divided by gamma plus t. It remains to compute the nth derivative according to t here, but that is easy because the t only appears in the denominator. So I get, so that's essentially something to the power minus 1. I get n times a decrease of the power here. So I have gamma plus t to the power n plus 1. The minus 1 to the n goes away, since we have the here to the power of minus 1, and when you put the power down, I get a minus 1 to the another minus 1 to the n, and minus 1 to the power of 2n is 1. I also get an n factorial because I make the nth derivative. And decreasing the power here, which is minus 1 by n, gives a power of minus n minus 1, which is the reason for this here. I have to validate it at t equals 0. That's also easy. N factorial divided by gamma to the power of n. Okay, that was straightforward, I would say. If you like, you can also try to compute the expectation of x to the power of n directly, not using the Laplace transform, and you will end up having many partial integration routes that you have to follow, and the computation is much longer. Okay, last for the normal distribution. So x is normal distribution. Oops. Okay, that was not intended. So this here is just psi. So the characteristic function is this here for the normal distribution. Well, let me make a few remarks here. So this formula is the same as this formula. And that means characteristic function, okay, I have the expectation here, I have the variance here, so this is here then straightforward, I guess. Yeah, I only have to keep in mind that in this case, the expectation of x squared equals the variance of x plus expectation of x squared, by some rule we had before. And this is sigma square plus mu square, which is the reason why I have one term sigma square here, one term mu square here. Yeah, so okay. But written differently, okay, what we had is, yeah, we had this here. Let's say t is small and we want to have a Taylor approximation. That gives me a 1. That gives me, everything which is in the exponent, it mu minus sigma square t square half. Then for the next term, I need a derivative with respect to t. Exactly. So when I do the Taylor approximation of this function with respect to t, I get, all right, I had already the derivative, which is it mu. For the second derivative, I can ignore this here because that will be a term of order larger than t square. But here, either it mu, I have to compute the second derivative, which is minus t square mu square, and the 1/2 comes from the Taylor formula. So I have this additional term, and from this here I can read off using this formula that mu has to be e to expectation of x, like here. And the variance is what's written here with the minus mu square, which ends up in having variance equals sigma square. Okay, I wanted to show here that using characteristic functions, it's also for the normal distribution easy to compute the expectation and the variance. Of course, you know that is mu and sigma square, which are the parameters of the distribution. But when you look back to your basic probability course, you computed this somehow, expectation of x equals mu, and that was a computation which involved many integrals, which we do not have here in this calculation. Okay, that's it for this video. Next time we are going to start with some convergences. Hope to see you there. Bye.